Today, we're going to dive into one of your body's most brilliant and, honestly, most overlooked daily miracles, making urine. Yeah, I know it sounds kind of simple, but it's actually this super high-tech process of filtering, balancing, and control that, no exaggeration, keeps you alive. So let's get right into it.
Okay, so let's start with something you've definitely noticed, right? Some days, it's almost totally clear. Other days, it's, well, a lot darker. What's up with that? It's not random. It's your body making a constant, second-by-second calculation that's absolutely vital.
And the answer is hidden deep inside a system that is so complex and so elegant, it's like a biological factory working 24/7. We're about to peel back the layers on this incredible piece of internal machinery. At its core, this whole process is about just one thing: balance. Your body is totally obsessed with maintaining the perfect amount of water, and your urine is the main tool it uses to pull that off.
And the sheer range of that control is just amazing. If you've had a ton of water, your kidneys can produce incredibly dilute urine, something like 1/6 the concentration of your normal body fluids. But if you're dehydrated, they can flip a switch and create urine that's almost 5 times more concentrated just to conserve every single last drop. I mean, what an incredible dynamic range.
So how in the world does the body pull this off? Well, to find out, we have to zoom way, way in and go inside the kidney's microscopic concentration factory.
Meet the star of the show, the nephron. You've got about 1 million of these tiny little structures in each kidney. And see that long hairpin loop that's dipping way down? That's called the loop of Henle, and believe me, it is the absolute key to this whole operation.
Now, to make concentrated urine and save water, your body needs 2 things. It's non-negotiable. First, you need a hormone called ADH. You can think of it as a messenger that basically yells at the kidneys, "Save water!" and it makes the final tubes more permeable. And second, and this is the really clever part, it needs to create a super salty environment deep inside the kidney that water will just naturally get sucked into.
Before we go any further, let's nail down a key term: osmolarity. Don't let the word scare you, just think of it as saltiness. That's it. It's a fundamental rule of biology that water always wants to move from a less salty area to a more salty area to try and balance things out. This one principle powers everything we're about to see. And check this out. This map of the kidney perfectly illustrates the challenge. The outer part, the cortex, has a normal saltiness of about 300. But as you go deeper and deeper into the medulla, it gets insanely salty, reaching 1200 or even more. This is the gradient we need. So the big question becomes, how on earth does the kidney build this thing and keep it there?
Well, the answer lies in that hairpin loop we just saw. It functions as this remarkable engine, a gradient building machine that almost seems to defy logic. Let's see how it works. The process is called countercurrent multiplication, which sounds super complicated, I know, but it's really just 2 simple steps that get repeated over and over and over. First, there's a pump, and second, there's the flow of fluid. That's it. Let's break it down.
Here's step 1, the pump. Take a look at the right side of the loop, the ascending limb. It's a total powerhouse that actively pumps salt out, but, and this is crucial, it's completely waterproof. Now, because the fluid outside the loop just got saltier, water passively leaves the other side, the descending limb, to balance things out. This one simple action creates a 200-point saltiness difference across the loop.
Okay, now for step 2, the flow. New fluid comes into the loop, and it pushes that slightly more concentrated fluid from the descending limb down toward the bottom. Then, the pump we just talked about in step 1 happens again at this new level, making the outside even saltier. This whole thing just repeats, over and over. Each cycle pushes more concentrated fluid further down the loop and actually multiplies that initial 200-point difference. It's like it's stacking the saltiness, creating that incredibly steep gradient we saw a minute ago. It's genius.
And there's a helper. To give the gradient an extra little boost deep in the medulla, the body recycles urea, which is a waste product. That same hormone, ADH, allows some urea to leave the collecting duct, which adds to the total saltiness and helps pull out that very last bit of water when you're really dehydrated. It's just an incredibly efficient system.
Okay, so the kidney has done its incredible work. The urine is officially made. Now we have to zoom back out and look at the final step, this really elegant system of storing it and, releasing it on command.
This whole process is called the Micturition Reflex. Really, it's just a constant, complex conversation happening between 3 key players: your bladder, your spinal cord, and your brain.
So here's how it works, step by step. As your bladder fills up, its walls start to stretch. These little stretch receptors send an alert to your spinal cord. The spinal cord responds with a basic reflex. It tells the bladder muscle to contract and the involuntary internal sphincter to relax. At the exact same time, a message shoots up to your brain, creating that conscious feeling of, hey, I gotta go. But, and this is the amazing part, your brain can send down a veto signal, keeping the voluntary external sphincter closed until you decide the time is right. It's this beautiful mix of automatic and conscious control.
And you can actually visualize this whole process with a graph called a cystometrogram. What's so amazing here is that long, flat line. It shows that as the bladder fills with hundreds of milliliters of fluid, the pressure inside barely changes at all. It's only when it hits a certain threshold, around 400 milliliters or so, that the reflex finally kicks in, and that's when you see that sudden, sharp spike in pressure.
Wow, we've gone from these microscopic loops in the kidney all the way to the neural reflexes of the bladder. So let's zoom out one last time and just appreciate why this complex, silent system is so incredibly essential.
You know, when you get down to it, this system is a true unsung hero. It masterfully maintains your body's hydration, which is fundamental to basically everything. That powerful osmotic gradient is also essential for cleaning all the waste from your blood. And maybe the most incredible part? All of this, the pumping, the multiplying, the signaling, it all just happens automatically, every second of every day, without you ever having to think about it once.
And here's one last cool little detail. Why doesn't the pressure build up while the bladder fills? Well, it's thanks to physics, specifically something called Laplace's law. As the bladder fills up, yeah, the tension in its walls increases, but so does its radius. These two things pretty much cancel each other out, which lets it hold a huge volume so comfortably. I mean, what a brilliant piece of biological design.
So we'll end with this thought. We've just explored this incredible, multi-layered symphony your body conducts just to manage its water balance. It really makes you wonder, doesn't it? What other amazing, invisible, and perfectly engineered systems are working tirelessly inside of you, right at this very moment?